Today's is the second part of this paper. So let's look at the title and cell tumbling enhance stem cell differentiation in hydrogel via nuclear mechanotransduction. The keyword is cell tumbling. You already know that moving, like moving inside of gel, they're rotating. And stem cell differentiation. Differentiation in chondrocyte before, and then later they are going to show us like adipogenesis and osteogenesis and cartilagenesis. And in hydrogel structure via nuclear mechanotransduction. So we already know that tumbling, they're performing around mini scale. And then in the second scale, the nuclear also tensioned and then stress. So cell can deform their local niche in 3 dimensions by whole cell movement, such as spreading, migration, or volume expansion. These behaviors occurring over hours that influence long-term their our previous knowledge, right? Spreading, migration, volume expansion, it occur over hours a day. But here we report the whole cell movement that occur in sliding hydrogel at the minute time scale. Minute time scale is opposite word compared to how hours a day. Term cell tumbling. Cell tumbling also another terminology over spreading, migration, volume expansion. Characterized by 3-dimensional cell dynamics and hydrogel deformation, elicited by heightened second to minute scale, such skeletal and nuclear activity. Studies inhibiting or promoting the cell tumbling of mesenchymal stem cells showed that this behavior enhanced differentiation into chondrocyte. Further, it is associated with a decrease in global chromatin accessibility, which require for enhanced differentiation. Actually, up to this sentence, this is the first part, and after further sentence, this is our today's part, which require for enhanced differentiation. The tumbling also occurs during differentiation into other lineages, and each differentiation enhancing effect are validated in various hydrogel platforms. Our research established that cell tumbling is an additional regulator of stem cell differentiation, mediated by rapid niche deformation and nuclear mechanotransduction. Briefly look at our previous finding. They are making two elastic hydrogel, but this elastic hydrogel SG they can allow sliding because this ring structure, the cell can slide and move this hydrogel. The CG chemically bonded one, cell cannot slide them. And then after 3 weeks of differentiation in chondrocyte, they found out that chondrogenesis occur a lot in SG. Then they checked their tumbling within 10 minutes, cell rotated, but CG doesn't. When they look at the ECM, hydrogel, some ECM, they are condensed locally, but CG, they don't have it. And then they quantify the speed of the rotation and the measure axis as an angular rotating speed. Then they want to know how much they move. Actually, the metric deformation is around 1 micrometer, almost zero from CG. The cortical actin, they need some bone kind of like structure, which is called cortical actin here. Cortical actin is highly expressed near the cell membrane. So cortical actin. And then when they measure the actin structure using live staining, live imaging of actin, they found out actin is like move faster, like within 30 seconds, they are moved. So compared to CG, SG, they are moved around by 5%. And then because of that, the nuclear also they rotated like this. And the nuclear is also moving along with that cell movement. And then also cell and nucleus, their movement, they're synchronized all together. Well, nucleus is more faster than cell by themselves. And then they check this kind of cell tumbling. Actually, they check at day 0, which means right after seating the cell inside of hydrogel. Well, they found out over time, this cell tumbling is gradually going down. So they focus on, and then the other matrix deformation affecting nuclear speeders going down. Then they want to know this kind of cell tumbling is very important for regulating stem cell differentiation in chondrocyte here. So they block this cell tumbling by blebbistatin, actomycin inhibitor, 1 day up to 3 day, and initial 4 day, middle intermediate, and final late stage. They found out that this earlier inhibiting quite diminished this chondrocyte differentiation compared to other one. So they found out this stem cell tumbling is quite important for regulating stem cell differentiation in chondrocyte. Okay. The next step is okay. So they want to know why, right? So they want to look at this nuclear epigenetic. So if you see some change of differentiation or some other migration or proliferation, for example, and then nowadays people want to look at the epigenetic change. What happens in nucleus? So when they check the nucleus, SG, CG, and SG plus blebbistatin is like similar to the CG because they block the cell tumbling. They found out that laminase is highly maintained, SG. H-chromatin, heterochromatin as well, and euchromatin very similar. So they found out that relatively heterochromatin-related laminase structure as well as K9-methylene 3, K27-methylene 3 are highly maintained in SG, while non-differentiated hydrogel HG and then cell tumbling blocking situation SG plus blebi, they diminished laminase other K9-methylene 3. But this euchromatin marker, they didn't change at all. So actually, if when you this is sometimes people say that this is a little counterintuitive because we think about the stem cell have a multipotent property, which means that they seems to have more euchromatin structure to differentiate other cell lineages. But here they found out that even though this SG has a higher potential to differentiate in certain lineages like chondrocyte, they show reduced chromatin accessibility, which means that they are more heterochromatic structure. So you have to think about that. Okay, you are a stem cell, but you are driving certain lineage, and then you have to turn off the other gene expression. Well, you have to turn on only chondrocyte differentiation related gene. In this kind of context, actually this is depending on the context, but here this context, when they reduce the chromatin accessibility, which means that they block other gene expression like stem cell maintenance or other cell differentiation lineage, but they only turn on the chondrocyte differentiation. That's why they show reduced chromatin accessibility overall. But while they overall turn off that accessibility, but probably they turn on the gene expression related to chondrocyte, right? And then when they look at this laminase, other kind of other ITC level, this is almost gone. Laminase is highly expressed in H and K9-methylene 27-methylene 3 as well. And then the beauty of the K9-methylene and 27-methylene 3 is that K9-methylene 3, most of them, they are acting as a repressing the gene when they are especially localized in H. While K9-27-methylene 3 is a little bit overall expressed. This is a well-known phenomenon. And then actually C, sometimes you just show C, the ICC images. But I strongly recommend you try to quantify like this, depending on the cell edge, you quantify the signal intensity like this, and then you can make more graph. And then people want to ask why you show like this. This own image is not enough. But in case when you think about this whole figure, this percentage of this figure is the meaning of how much is important. If you only show this C, only this graph, only this image is not a graph, which means that this C is just, this portion is important. But when you show C images and quantification as well, and then this is a 1, 2, 3, 4, so we can say this is 25% important finding from this, right? So depending on how much important of your result or your something, you have to determine how much percentage of figure multiplication you are going to use. Okay, this is very important. Just show the data is not enough. Depending on how much is important, about how you show them depending on the importance of the result. And then they check the ATAC sequencing. ATAC sequencing is checking which site is more open or closed from DNA. So and number two, CG and SG, this is the PCA analysis you can do easily using bio and using X data, bio. There, here, depending on change, you can see most of the chromatin accessibility is downregulated, which is because fold change is going down below the zero, and then you can see this kind of red color in chromatin accessibility, and then they look at this CG and SG. Also here, G is top 50 genome region that are statistically significantly different between SG and CG here. And then p-value below 0.01 and fold change over zero point 0.5. So here they showed us highly accessible in CG. Actually, if we pick up the only chromatin accessibility downlink in the CG, this right side is gonna be show blue color, left side is red. This panel they just show they highlight their chromatin accessibility is down here, but they show us the unregulated part. Probably if you go supplementary, they also show us downregulated part in CG. Why they are doing that? If you only highlight the downregulation, but you can explain how the CG can increase the differentiation. So here, as a counter, they show like this. And then they also want to know this heterochromatin increasing. New chromatin things that can affect our constant differentiation of stem cell. They co-treated with acylcarnitine with methanotrexate inhibition. Catocin may inhibit carnitine. What? SG has higher circularity level, but they want to decrease. And then they like CG and they want to know how these things happen. Sorry, I mislead you. SG is our thing, right? SG is our tumbling. They show us close chromatin accessibility. So that's why, along with the previous one, they highlight here only show us decreased chromatin accessibility. But actually, if you show here, something is also can go up, but they only show us like below one using this cutoff like 0.01 value and certain local change. And then when they mimic the chromatin structure similar to the CG, even though they culture stem cell in SG, they found out chromatin 3 inhibited. They show decreased chromatin differentiation. But interestingly, this Gaussian, even though they didn't change at all between these two groups, inhibit the acceleration also decreased. So maybe I believe that this is coming from the review comment. They just suggest you try to treat this Gaussian to confirm isolation is really no meaningful one. But here you can show them they are meaningful to differentiate, to control differentiation. So when you look at the manuscript, they just simply write down. Also, isolation doesn't change that much by the cell, their deformation, but isolation itself also they govern the cell differentiation. But it's not very major driving force from the hydrogel. Yeah, so like this, even though you can see some like very not solid result or outcome, which is not fit your story, it's fine. You cannot 100% truly say A, B, C, this kind of medically link some phenomenon. Sometimes there are some messed up like this. Also, people also understand it. It could be like this. Then they look at the nuclear tension. So I'm not sure you guys are so familiar with the nuclear tension. So when you look at the 2020 science paper, the first report, nuclear itself, they can sense the tension. So the special mechanism that when nucleus is tension like this, stretched, and the PLA2 is activated, and then this ARA, this like arachino, arachidonic right exit, they release from the nucleus, and then this IRA they can enhance the cortical ectomachic contractility. That is why this very well-known phenomenon from 2020. So they imagine why cells are good because they have higher cortical contractility, affected structure. So that's why probably this kind of mechanism could happen here. So they look at the PLA2 level. PLA2 level is highly condensed, like here, within 6 seconds. And then this kind of percentage of change in area, they're quite a lot in SG, CG. And then average nuclear area fluctuation, this relatively flat, they are a little curve like this, but this is relatively maintained like that. So this average percent change in area. Do you know what I mean? 0.4 means 0.4%. Very small. But you have to question of period 2. They found out compared to control, SG higher, CG go down. Blabistatin, they block the tumbling. They are all gone. So this is their quantification. Also, when they change this PLA2 inhibitor, they go down. When they add ARA, as a result of a PLA2 activation, ARA is secreted to activate cortical actin activation. So there's some increase. But when they change this CG hydrogel, whether they treat PLA2 inhibitor or ARA, they didn't show that much of a change. From the center speed of the cell, the speed as well. To initial differentiation point, also they are decreased, while ARA, they are somewhat enhanced differentiation. So here they want to say that this tumbling mediated, tension mediated, actin contractility, something happening. This is very important for stem cell differentiation in cartilage. As the last features, not only chondrocyte, they want to check kind of same thing could happen in other stem cell lineage differentiation. So actually, they all the time they culture the MSC right after adding the cell in hydrogel, and then they culture them in chondrogenic differentiation media, not cross media. Here, in the same manner, right after adding the cell in hydrogel, they change the bone differentiation media for A, adipotenic differentiation for C, and cartilage. So when they look at the cell tumbling again in autogenesis differentiation media at day 0, they still find out central speed, measure axis speed, they are changing that much. This is differentiation, like 2 or 3 weeks later, differentiation is highly detected in SG. Same thing happened of nuclear tumbling or cell tumbling, hypotension is highly increased in SG. And then actually they use SG and CG, different gel. So they are making other gel, same CG, but they change certain component of the CG and then they allow CG degradable. So they are making degradable CG. They have similar thing happen because when they allow degradation of gel, cell tumbling could happen. So because of cell tumbling, cell differentiation in cartilage more detected. And same thing, they are making viscoelastic gel, CG. CG, same component, but they are little shift structure component. And then same thing. So this is another way. Okay, when you show the SG only, and the people will argue about SG and CG, they have totally different, maybe little like percent different, but they have different composition. So, and in that case, you better to show us when you use another hydrogel that can allow tumbling, same thing happen. So they prove it, support your data again. And as a final scan images, when stem cell are localized in 3D structure, and they allow this cell tumbling inside hydrogel, local matrix reorganization happen while they're tumbled. When you look at the cell matrix interface and the nuclear interface, and then there are dynamic characteristics that can occur. So matrix deformation as a mini scale, you can detect it. And effective dynamics, second scale, detect. Nuclear deformation also very second scale. Nuclear movement also happen. So here, chondrogenesis, the other you can apply this PRA signaling. This is well-known signaling by tension. That even they are this look and the after change happen, drive the stem cell differentiation in certain lineage. This there major. Now let's look at the expanded here. How is major figure, extended figure, and complementary. Like in the end, actually, uh, as an initial point, they are making 12 figure, and then key figure located in major figure. Little like not important figure in extended data figure, but this is still important. Then when you see another like non-important, but it's essential to show us that could be added in supplementary. Now we're going to make this kind of three different category of figure. So extended figure one, differentiation of cell tumbling and nuclear movement upon cytoskeleton inhibition and link complex inhibition. This is easily we can ask. We are highlight actin, right? So if you block the cytoskeleton using BLIB, we already did. Cyto-D, affecting depolymerization, Y27, RAG inhibitor, what happened? All the cell tumbling is going down. When you also block the link complex is linking nucleus and actin. Nucleus membrane actin, they need some linker in the between. So this is like DN cache. DN cache is just some plasmid, and that can only be activated by doxycycline. So doxycycline is added, which means that this DN cache, they block the linker between actin and nucleus membrane. So here, when they transfer active DN cache, and there's no activation by doxycycline, it's fine. But when they activate the DN cache, they are losing link complex, and then this oral cell tumbling is going down. The next, they want to look at the focal adhesion protein like paxillin, vinculin, FAK, fibronectin. Actually, in 3D structure, it's not easy to see this kind of focal adhesion protein near the affectin. When you culture the cell in 2D, focal adhesion protein, you can see a lot between actin, edge of the actin. But this is 3D. So they are located in near cytoplasm, right? But which didn't mean that this is really inside of the cell. This red color, this is like your outer surface, almost outer surface of your cell. Okay, so you can imagine this is a 3D, and then you can G-stack and then compile them all together. So this is not 2D. Think about 3D, even though this green color is located inside the cytoplasm, in the cytoplasm. This is located your outer cell membrane. Okay. Anyhow, this paxillin, vinculin, other thing is highly detected in SG compared to CG. And then they want to know what is the role of this protein. So soluble RGD, which is competitive manner. SG has already RGD structure inside the gel. So when they add soluble RGD, this soluble RGD, they compete the RGD inside of the hydrogel. So when they add the soluble RGD, the cell cannot 100% recognize the RGD in hydrogel. It's kind of blocking, right? This is called competitive blocking. In this manner, these cell terminals go down. When you remove the RGD in hydrogel, also going down, CG is a control. So its focus in protein is also quite important for regulating the cell tumbling. This should be true. Cell needs some binding force to rotate, right? They cannot rotate by themselves. They have to put and push the ECM, and then using that force, they have to rotate, right? So this is a very easily you can ask the question. So that's why they put it in supplement, this extended figure. And then they want to look at this, one of the complex called arginine. Actually, you can see another like the link complex like aspirin or arginine or other kind of link complex you can highlight. But here, as a representative, they focus on arginine. Arginine is highly detected in SG, CG less, NSC is their arginine inhibitor. They're going down. So when they look at arginine, very cortical edge area arginine high detected. And then when they treat NSG, actually it's not very solid here, but compared to this one, relatively dim at the edge. So when you look at this kind of link complex protein, laminase, aspirin, you always have to focus on edge area of nucleus, right? Not overall. But CG control, they show very deep structure. And then when they check this arginine, also same thing happened. Cortical actin, here they're gone, and then cell tumbling speed also gone, right? And then also people ask you, okay, previously they show us these actin inhibiting things, they decrease cell tumbling. So they want to know this cell tumbling decreasing can induce less differentiation in chondrocyte. Chondrocyte-related gene expression level highly decreased in this inhibitor, and then as a differentiation, staining, same thing happened, right? The last one, they want to confirm again, this lower of this link complex. Such 9 American collagen 2A1, they all go down when they block the link complex. Okay? And then this here. This one, when they block it, they go down. And the last one, actually this is a little not solid here. This RGD, soluble RGD, without RGD, they decrease the cell tumbling, right? But from the gene expression level, they didn't change that much. From differentiation also, what just happened? Actually, this is like chondrocyte. Actually, chondrocyte, they don't need cell binding, right? So for the final differentiation, because it's a chondrocyte, this soluble RGD, and without RGD, they can show similar thing. But why they are showing this? Because but when they show this similar result from bone or from adipogenesis, probably this all of them they should go down. From this is chondrogenesis, so they show here even though this is not going down, but because this is chondrogenesis. Yeah, chondrogenesis actually the cell binding doesn't necessary that much compared to other differentiation. Okay, this is the last of this paper. So any question? Comment? Mm-hmm.
It's got done on hydrogels.
Yes.
And they had linker molecules in each in the first figure.
Mm-hmm.
Had two different gels, that is SG and CG.
Yeah, right.
SG had linker molecules
Mhm.
and CG didn't. If we could have this in like a rigid physical topology,
Mhm.
could we repeat the experiment?
Yeah.
Doing like one with having more minor groovings and one with plain groovings.
Mhm.
We repeat this in that case.
Yeah, that's a very good question. So actually, as you remember, their stiffness around like, as you probably remember, four kilopascal, something like that. 4 kilopascal, quite relatively soft one, right? So your question is, if you culture the like, uh, I think that after referring the other literature, maybe compared to even though we are 4 kilopascal, maybe let's say if you culture them 4 megapascal, and then you allow the sliding, non-sliding, only stem cell they cannot differentiate. In chondrocyte and other things, they cannot move at all. But in case of 4 kilopascal, maybe some tendency you can see that. So for example, this is like 4 kilopascal and 40 and maybe 400. But this kind of difference, maybe this CG always they like white one, but this red differentiation, little dim 40, and then they're gone for 400, something like that. So in street structure, first first determinant is stiffness first also. But also you have to consider this kind of allowance, cell movement allowance. Since 2015 or 16, after the Chadri group, David Mooney, they wrote about stress relaxation. So, so also that paper, they exactly the same manner. They are using three different stiffness and then three different stress relaxation, fast and slow. They found out that faster, anyhow, they show some differentiation, but more like in terms of bone generation, bone differentiation, higher stiffness, they can differentiate better. Right. So this is depending on the which kind of differentiation you are expecting, and then which kind of stiffness you are using. Yeah, but definitely we can say that stiffness also can have a role to regulate the center differentiation. Mhm. So I think if you think about this is a stem cell, and then they only checking on the differentiation condition, right? So they look at us, their heterochromatin is highly maintained, while CG they going down the heterochromatin, which means they are more euchromatin, right? They are still stem cell, right? So when they differentiate the stem this SG is important. But when you think about another point, when you want to maintain stem cell with their more stemness for longer time, which one can be better? Probably CG, right? Yeah, CG they can maintain the structure, they did differentiate, right? But this is like they can only detect the chondrocyte differentiation media. Probably next paper, well, they're gonna show us like when they culture them in growth media, like stemless media, which one's better? And then you can aim like another paper. Probably the impact is not that much because they already use this material in this project. But when they shift your point to stemless, and then probably physics could be better or SG, not sure, but maybe they are going to study. Probably can expect. And then when you culture the cancer cell or macrophage, what can be the best? And then you can enlarge. So once you develop a material like this, based on the good question, and then you can enlarge your whole experiment in a good way. Okay, thank you. And then